For a rocket to fly stable, you need 1 caliber of stability. Or 2, or something like that. This is the classic rule that you use to design high-power rockets. That's how I designed my first high-power rocket, Surveyor, which flies great at just over 1 caliber of stability. But recently, Nick from Lafayette Systems launched his Airbrake Rocket, which had 1.1 calibers of stability, and this happened.
Hey, good flight! I got a parachute!
If you haven't seen his videos, you should absolutely check them out. He does a ton of active control rockets. This one's actually passive stability, but he has active controlled air brakes, which try to hit an exact altitude. In theory. So let's get the obvious question out of the way. Were the air brakes the problem? Well, probably not. In theory, they shouldn't be opening until later in the flight when it's well clear of the launch rail, but we can't know for sure because the onboard footage was lost when it hit the ground. Now, if we look at the second flight, which was actually stable, more on that in a second, we can see that yes, the air brakes do wait to deploy until it's well clear of the launch rail, so yeah, probably not the actual issue. He also mentions that there's cameras and rail buttons sticking out, which could cause some aerodynamic funkiness, though Surveyor also has those, and if anything, it's worse because my camera mount is the exact opposite of streamlined. So, back to his second flight, what did he actually change? Nick increased his static margin from about 1.1 to 1.5, and he did this in 2 ways. 1, by increasing the size of his fins, and 2, by adding mass to the nose of his rocket. Static margin is just the distance between your center of mass and your center of pressure. Adding mass to the front of the rocket moves the center of mass forward, and increasing the size of your fins moves the center of pressure backwards. What is the center of pressure? Well, if you take all of the aerodynamic forces acting on a rocket and you add them together, the center of pressure is the point where they all meet up. You want that center of pressure to be behind your center of mass, which is the point the rocket rotates around. As a rocket is wobbling back and forth, it creates an angle of attack, which is an angle between the rocket and the wind. As long as your center of pressure is behind the center of mass, as it should be, that is going to generate torques which restore you back to vertical. For drag, the drag is pointing straight down relative to the wind, so you can see that if it's on the left side, it generates a torque turning it to the right, and if it's on the right side, it generates a torque turning it to the left. But that's a small effect. The larger effect actually comes from lift. Lift, generated by the fins, increases as the angle of attack increases, and importantly, it's acting perpendicular to the wind. This means it generally has more leverage, and that leverage depends on your static margin, the distance between where that lift is acting and your center of mass. Which is why, if you increase your static margin beyond 1 caliber, you can improve your stability. You're giving it more leverage. Also, you might be wondering, what is a caliber exactly? Well, it's just a way to normalize this distance. Instead of talking about it in inches or millimeters, you take that static margin and then you divide it by the diameter of your rocket. This has worked as a rule of thumb for years, possibly decades, but why diameter? I mean, if I make my rocket an inch wider, does it actually need the extra inch of static margin? Well, maybe it's something to do with mass, larger rocket could be heavier, but that's not necessarily true. I mean, a 3-inch fiberglass rocket can be a lot heavier than a 4-inch cardboard rocket. Maybe it has something to do with drag? But then again, I've already pointed out that drag at small angles actually helps your stability, it doesn't hurt it, so I don't think that's it either. And yeah, it turns out that we do throw out the caliber rule, especially for short and wide rockets. You can have some better luck with percent stability, which takes the static margin and divides it by length instead of diameter. If you want to try that method out, you should be aiming for a static margin, which is about 8 to 15% of your total length. Honestly, I don't know why we didn't start there. It makes way more sense to me. But that doesn't really explain why Nick's rocket performed so much worse than mine when we have the same static margin. It's not like he has a crazy length to diameter ratio, it's 11. That's very typical, and it's identical to Surveyor. I don't think that the issue was static margin at all. I think the issue was dynamic stability. And to explore that, we're going to have to look at some simulations. There's more to torque than just leverage. You also need force. Small fins could have the same static margin, but because they generate less lift, they're going to generate less torque. Static margin just tells you where that force is going to act. It doesn't tell you how strong it is or how quickly the rocket's going to respond. To understand that, it might help to look at the rocket like a mechanical system. Let's take another look at the animation. As the rocket tilts back and forth, it increases the angle of attack, and that increases the restoring force. It increases roughly linearly, at least for small angles, which means it's acting a lot like a spring, ignoring other factors like wind speed and air density. So I made a simple model of the rocket that treats it like a spring. It's wobbling back and forth at a constant frequency known as the natural frequency. If I increase the strength of the spring, which is analogous to increasing the size of the fins, it swings back and forth faster at a higher natural frequency. But right now, the rocket is just wobbling back and forth forever. We need another component known as a damper. While springs are elastic and they're just generating forces trying to push you back into position, dampers are actually removing energy from the system and trying to resist motion. For a rocket, this damping comes in the form of aerodynamic forces which resist rotation. So if I add just a small amount of damping to the system, you can see it overshoots, but then the magnitude starts to decrease and eventually it settles out around zero angle of attack. In engineering terms, this is what we would call underdamped. If I increase this damping, I can eventually reach a point known as critically damped, where the rocket doesn't overshoot and it smoothly returns back to zero. If I increase damping further, we become overdamped, which means it responds more slowly and it doesn't quite reach zero. Now you might think that we want to increase this damping until the rocket is critically damped, but that's not actually ideal for rockets. When your rocket has some angle of attack, it doesn't just rotate back vertical, it also starts to move in that direction. So if you have too much damping, your rocket can actually slowly arc off course. But if you intentionally leave it underdamped, it will overshoot back the other direction. And that overshoot does a couple of useful things. One, it reduces the amount of time that you're spending on either side of vertical, and two, it helps cancel out the drift. An underdamped rocket sort of slaloms upwards and averages out around vertical. Also in practice, you can't really overdamp a rocket without active control or maybe some non-standard fins, because increasing your fin size does increase your damping, but it also increases your natural frequency, and damping ratio is a function of both. The only non-standard fins I can think of which would increase your damping without increasing your frequency would be something like strakes, which are near your center of pressure, meaning they don't contribute any restoring torque, or canards, which are ahead of your center of pressure, and that means they contribute negative restoring torque. But so far this has all been conceptual. To get some actual numbers, we're gonna have to go to OpenRocket, which is a bit more grounded in reality. OpenRocket isn't perfect, like any model, but it is useful. It's based on the Barrowman equations, which are fairly simplified calculations, which generally apply to traditional-looking rockets. For our purposes, it's good enough to be able to make some comparisons. So what I did was model two basic rockets. They're almost identical, just one has fins that look like Surveyor, and the other one has fins that are half scale. Otherwise, they're completely identical. They have the exact same mass, and they both have exactly one caliber of stability. OpenRocket is going to simulate a flight for each of these, and to keep things consistent, I set the wind to be 10 miles per hour with no variability. That's a fairly realistic number. It's below the safe limit of 20 miles per hour, and it should be enough to give us a little bit of a kick right at launch. And what I'm gonna do is go here and export the data from OpenRocket, and that's gonna let me compare them by plotting them next to each other using Octave. Octave is like a free dupe of MATLAB. So this is the angle of attack data for the two rockets. If I zoom in on the interesting part of the flight, it's not exactly a clean sine wave, mainly because it's rectified. The reason that's happening is because OpenRocket is giving us the magnitude of total angle, instead of breaking it up into pitch and yaw components. Now those can be useful, but for our purposes, we really just want to look at the magnitude right now. It's a little bit chaotic, but if we zoom in just on this section, which is 1 to 2.5 seconds, we can compare the two rockets. Blue is the big fin rocket and red is the small fin rocket. You can see the big fin rocket has a lower magnitude and it's decaying more quickly to my eye. And the red one obviously has higher magnitude, but you can also compare the frequencies. You can see that the blue peaks are happening more often, which indicates that it has a stiffer spring, going back to that analogy. So let's quantify this. I trimmed the data so it starts after we're clear of the rail, but then ends a few seconds before apogee, which is the point where the rocket's going to slow down and become unstable. The rail is really critical here. Its whole purpose is to keep the rocket vertical while it gets up to speed, but it's only after we're free of the rail that the fins are actually doing anything. This also seems like a good time to point out that OpenRocket makes some very idealized assumptions about launch rails. It's not accounting for friction or wobble or anything like that. In reality, all of those factors can give your rocket a little bit of a kick right when it leaves the rail. This is known as rail whip, and that's something you should really be considering when you're designing your rocket. But anyway, back to the angle of attack data. If we look at these peaks, we can learn two things. By counting them, we can learn our natural frequency, and by fitting an exponential curve to them, we can figure out our decay rate. Combine those two and we have our damping ratio. But when I did that, I found out that both rockets have about the same damping ratio. It's around 0.1. Now yes, larger fins will create more drag and more damping, but they also are a stiffer spring, which means a higher natural frequency. Because your damping ratio is a function of both, it kind of makes sense that you end up with the same result. But when we look at this data, we can clearly see that the big fin rocket is stabilizing more quickly. That tells me that the damping ratio isn't what we actually care about here. We should be looking at the decay rate. So let me pull up the decay curves here. This is starting at 5 degrees and showing how they dissipate over time, and it is clear as day. The big fin rocket is stabilizing more quickly. But let's see what happens if we increase our static margin. I'm going to do that by grabbing this payload component and moving it forward in the rocket. Normally you would just add mass to your nose, but again, I want to keep the mass the same between these two rockets, so it's a direct comparison. So let's skip this raw angle of attack data, just go straight for the decay curve. And it's not looking great. The yellow curve here is the one with 2 caliber stability, red is 1 caliber stability. They're pretty close. The yellow one is below it, so it is helping a little bit, but it's nowhere near the blue line, which again is the larger fins. If I just take a slice here at half a second, yeah, you can see that it moved the magnitude down a little bit, but nowhere near what larger fins will do, even though we've doubled our static margin. I find this really interesting because it's very common in rocketry when you have stability issues to add nose weight to increase your static margin, but this shows us that there's diminishing returns. Increasing static margin is not improving your restoring force, it's just giving it more leverage. Alright, I just want to make a quick note here. First, when I have the scale of the fins for the small fin rocket, it actually meant that it had a quarter of the fin area. So knowing that, maybe you're thinking that doubling the static margin just wasn't enough to fix stability. But I can check that. I can cheat and crank the static margin all the way up to 4. But that doesn't make the stability better, it actually makes it worse. Which brings me to my second point, which is moment of inertia. I'm going to talk about this more later in the video, but increasing your moment of inertia ends up hurting your stability, which is why moving the mass forward or adding mass to your nose isn't nearly as effective as increasing the fin area, and why it can actually make stability problems worse. Okay, now back to the original video. So while static margin is a useful pass-fail check for something like safety, it isn't really telling you anything about how a rocket is going to respond to a real disturbance. On the other hand, decay rate is actually telling you how a rocket responds to a disturbance, and increasing that might require a fin redesign, not just a center of mass change. However, you can overdo it. When the rocket leaves the launch rail, it's released into the wind, and it's going to start to turn into the wind and arc over. This is known as weathercocking, because the rocket's acting like a weather vane, also known as a weathercock. There's a lot of things that influence this phenomenon, including wind speed, launch rail length, thrust-to-weight ratio, but also the rocket's design and stability. A low thrust-to-weight ratio and/or a short rail is going to decrease your vertical velocity when you leave the rail. The slower vertical velocity means that the wind coming from the side is a bigger proportion of your total velocity. Long story short, you're going to have a higher angle of attack, and your rocket's going to turn even harder into the wind. Highly stable rockets with very fast decay rates are going to have the same problem. They're going to turn into the wind very quickly before they have time to build up speed in the air. But generally this only really happens when you have multiple factors stacked on top of each other, like large fins, low thrust-to-weight ratio, a short rail, and high winds all at the same time. Also, it can be worse if you have those non-standard fins like canards or strakes, which increase your damping. Generally, increasing your thrust-to-weight ratio is probably going to get you out of this problem because it's going to get you up to speed faster. Another big problem with overstable rockets is coning. This is a little tricky to describe. It's especially common with 3-fin rockets because their forces are less symmetrical, meaning that the net restoring force isn't always pointed straight back at center. This asymmetry can trigger an oscillation mode where pitch and yaw are coupled but out of phase, resulting in a motion sort of like this, where your rocket's moving around in a cone. That's why it's called coning. Lots of stability will mean a higher natural frequency, which can exacerbate this issue. When I was planning this video, I actually reached out to Nick from Lafayette Systems to see if it was okay to share his footage. When I did that, he also shared some of his thoughts on dynamic stability. First, he brought up moment of inertia, which I haven't talked about yet, but it's essentially the resistance of a body to rotation. It's like mass, except for rotational movement instead of linear movement. With all the electronics and extra hardware that he packs into his rockets, they tend to be heavier and have higher moments of inertia than your typical rocket, and that will impact your stability. He also talked about limitations with OpenRocket's aerodynamics model. In particular, he's worried about the airflow close to his body tube. In real life, there's going to be what's called a boundary layer around that tube, which is a layer of slow-moving air. That means that the part of the fin that's right next to the body tube is way less effective than the tip. And he has highly tapered fins, which means most of his area is close to the tube, so he's worried that his fins might be underperforming versus what OpenRocket predicts. Now, there's nothing I can do to fix the aero model in OpenRocket, but what I can do is explore moment of inertia. What I did was make 2 copies of the small fin rocket with 1 caliber stability, except I overwrote all of the components and gave them 0 mass, except for the motor. Then I added that mass back with these 2 payload components, and moving those around allows me to change the moment of inertia without changing the mass. Having them right next to each other, like in this simulation, is unrealistically low. No rocket you can physically build will ever have a moment of inertia this low. In the other one, I have them far apart. This isn't necessarily unrealistic, but it's about as high as you're ever going to get your moment of inertia to be, at least at this weight. You can always make your rocket heavier, which also increases the moment of inertia, but right now the mass is the same between these two. Aerodynamics are the same, motors are the same, and they both have exactly 1 caliber of stability. And if I go ahead and pull up the decay curves, they're pretty similar. The blue line is the low moment of inertia, and it is decaying a bit more quickly. That matches Nick's prediction, but yeah, it's not a huge effect. Now, it's worth noting that this is based on the first flight of Surveyor, which was mostly empty. It had a single parachute in an empty payload bay, and it was missing a lot of extra hardware, which it had in second flight, and it definitely didn't have air brakes and servos and flight computers, which is stuff that goes into Nick's rocket, which makes its mass overall higher and would increase the moment of inertia more than the distribution of those components. That makes me think I should do a comparison. So I'm going to do this one live. I'm going to increase these 2 masses. Right now they're 578 grams. Let's just make them both an even 800. And then I'm going to have to move them around to get 1 caliber of stability back. Okay, I'm doing this one live. I haven't actually seen the results yet, so let's get a live reaction. Let's see what increasing our mass by about 500 grams. I think if I'm doing my mental math right. Oh, that made actually a pretty big difference. To orient yourself, this yellow line, which is not decaying nearly as quickly as the other 2, is the high mass. That's with the extra 500 grams of miscellaneous payload. That is a very interesting result. I think that might be a significant part of what happened to Nick's rocket. So why didn't the Airbrake rocket fly like Surveyor? Well, it's going to be a combination of everything we've talked about so far, but most significantly, the small fins. Straight off the rail, there's going to be a disturbance from wind, rail whip, and asymmetric forces, and the small fins just don't have the authority to fight that. And eventually it pitched past 15 degrees, which stalls your fins, and from there it's just flipping end over end until it can eventually slow down and restabilize. Of course, everything here is said with the benefit of hindsight. Dynamic stability is very complicated, and even in this short video we're already hitting limitations with the simulations we have available. So yeah, no 2 rockets and no 2 flights of the same rocket are ever going to be exactly the same. But at least you have an idea of what to keep an eye out for. I'm Con Happy, and I'll see you in the next video.